if you were to take the Laplace transform of a derivative, if you were to use integration by parts, we could say that u is e to the minus st, dv would be f prime dt. And if we were to differentiate this, we're going to be differentiating with respect to t, so we'll get negative s, e to the negative st, dt, and this would give us an f. And that's the point of the story here. So when we were to go ahead and use integration by parts, we'd have our uv, so we'd have f e to the minus st. This has to be evaluated from 0 to infinity. Subtract integral of v du. Now with the negative sign there, that'll become a positive, and we'll have s e to the minus st. This is a constant with respect to the integration variable. And that thing in the integral is just the Laplace transform of our function. In order for all of this to work out, what we need is for this first term to exist. And if you think about it, this is like saying the limit as t goes to infinity, f of t e to the minus st, subtract e to the 0, which is f of 0. Now, the only way that's going to exist is if the function is of exponential order. The only options here are to say, look, if s is positive, that means this exponential term will decay to 0. If that s term is negative, that's going to go to infinity. There's nothing we can do to control it. So we want s to be positive, and then because this function is of exponential order, it's going to die. It cannot grow faster than the exponential will go to 0. So this whole term will go to 0. And at the end of the day, what we have left is, if you were to take a Laplace transform of a derivative, what you're going to get is the Laplace transform of the original function, f of s. There'll be an s in the front of it. Subtract the initial value. When you take the Laplace transform of a single derivative, it converts everything into an expression in frequency space with no derivatives. That's the magic of the Laplace transform. Now, we don't have to stop at a first derivative. If we were to take the Laplace transform of a second derivative, and we assume that f and f prime are of exponential order, and if we take s to be greater than 0, the frequency to be positive, which is a natural assumption here, you're going to find that the similar pattern works out. For a second derivative, you're going to get 2 powers of s out front because you're going to have to use integration by parts twice. Then you'll get a power of s attached to that f of 0. Subtract another f prime of 0. In general, if you want to take the Laplace transform of an nth derivative, you're going to have to use integration by parts n times. And you'll get s to the power of n, f of s. And now you're going to go through each initial value of the function. It'll decrease in 1 for the power of s that goes in front as the order of the derivative increases. So we'll have an s n minus 2, f prime of 0, and that pattern is going to continue all the way down. So there's the n minus 1th derivative minus the n minus 1. Now, to try to see how this applies and how it helps us with differential equations, let's talk about a simple initial value problem, y double prime plus 9y equals e to the t, and we'll start at rest. Now, normally, what we have to do is say, look, I know the solution is going to be a homogeneous part and a particular part. I have to find this with e to the lambda t. Here, I'd have to use undetermined coefficients or Green's function, whatever the case is. You don't need to do that with Laplace transforms. It's all done automatically. So there's no need. Here, what we do is we take the Laplace transform of both sides. And what really saves us is that Laplace transforms are linear. So we use the linearity of the Laplace transform. This allows us to split things up, pull out any constants that we need, and get to this expression here. For the Laplace transform of the second derivative, what this will give us is an s squared capital Y of s minus s times y of 0 minus y prime of 0. So that all comes from that second derivative term. The other term here is going to be 9 times the Laplace transform of the function itself, which is exactly what happens here. And then last time we spoke about the Laplace transform of this exponential function. So this last term is just going to be 1 over s minus 1. Now here's the nice thing about Laplace transforms. All of the initial conditions get built in, and that comes through that derivative term. Now here the initial conditions are just 0. So this term will be 0 and this term will be 0. But if they're not given to you, so if there are no initial conditions, you're going to set these to C1 and C2. And that way you can even get general solutions when you use the Laplace transform. Now we start to see the algebra that comes about in using Laplace transforms. We take a problem from time domain, we convert it, we translate it or shift it into this physical space or frequency space, the S universe. In S universe, my differential equation turns into an algebra equation. Now, if I was stuck in S universe, I'd be done. I found it. This is the Laplace transform of my solution. But that's not okay because I didn't start in S universe. I have to convert back to T domain. Y of t, and y of t will be the inverse Laplace transform of this expression. So I have to take the inverse Laplace transform of this mess. Now, the only way I can do this is by using partial fractions. Now the idea with partial fractions is I'm going to take this ugly looking expression and break it up into what are called proper fractions. Each one of those proper fractions will have the same denominator as these components. Proper fractions say if the bottom is degree 1, the top can be 1 degree less at most. In this second case, the bottom is degree 2, so this will be degree 1 at most, bs plus c. If I were to put everything over a common denominator, this is the idea. And now everything here has the same denominator on both sides. What makes my life a little bit easier is that now I can equate the numerators. If these two expressions really are going to be the same, then their numerators need to be the same. And because of that, you're going to see that there are multiple ways of obtaining these partial fractions. We could solve by the system form, where you group powers of s, but I'm going to try a different way. We're going to use what are called test values. If these two expressions really are the same, they should hold for no matter what value of s I pick. So I'm going to choose convenient values. What do I mean by that? I'm going to say, well, when s is equal to 1, when s is equal to 1, what this is going to give me is an expression that looks kind of like this. And that's going to be a 0. And that's what I mean. I chose s equals 1 deliberately so that this second term will turn into 0. That part will be gone. And I'll be able to find out immediately that a is 1/10. Okay, that's great. The other value that I'm going to use is s is 3i. And you say, well, why on earth would you use s is 3i? Because if I pick s is 3i, that is the magic term that's going to get rid of that first expression with an a. We have to do a little bit of complex arithmetic. This is going to be 9 plus 9. That whole thing is going to go to 0. And I'll have 1. Now over here, I'm going to have 3bi times 3i. So when I multiply those two together, I'll get negative 9b minus 3bi plus 3ci minus c. Now remember, over here on this side, I have a 1 plus 0 bunches of I, and I'll have negative 9b minus c plus 3 into c minus b I. So what this tells me is that all the real parts have to be equal and all the imaginary parts have to be equal. So there are 0 imaginary parts on the left, and that 0 is going to have to be the same as this on the right. There's 1 real value on the left. It's going to be the same as this on the right. From this bottom term, I'll find that c is equal to b. And from this top term, I'll find that 1 is negative 9b minus another b. So b is negative 1/10. And that means that c is negative 1/10 as well. Way back when, you might have forgotten about it already, but the thing that I was looking for was the inverse Laplace transform of this expression. And I used partial fractions to try to convert that into 2 smaller fractions, like I did over here. I found that a was 1/10 s minus 1, and then I had bs plus c. So it'll be negative 1/10 s minus 1/10. All of this is over s squared plus 9. I'll have 1/10 Laplace inverse of this minus 1/10 Laplace inverse of s over s squared plus 9. Subtract 1/10 Laplace inverse of 1 over s squared plus 9. I know right away that the inverse Laplace transform of 1 over s is e to the minus t. E to the plus t. I know that this next term, the inverse Laplace transform of this, is going to be the cosine of 3t. And over here, if I were to put in a 3 up top and a 3 down below, what this is going to let me do is take out one of these factors of 3, the one in the bottom, take it out front, and that's going to give me negative 1 over 30 inverse Laplace transform of 3 over s squared plus 9, which is going to be negative 1 over 30 sine of 3t. And that gives me the solution according to Laplace transforms. I'll have this e to the t minus 1/10 cosine of 3t minus 1 over 30 sine of 3t. Now, this may not seem like an advantage to doing it the other way, but the real power of using Laplace transforms to solve DEs is because they can handle discontinuous functions a lot more straightforwardly than our traditional standard methods. So I'll be talking next about how they do that. And there's one tool that helps us do that, and that's the unit step function.